G'day everyone, and welcome to our lesson on the strength of the magnetic field and flux, two terms that are very important in electromagnetism. We're going to talk about the strength of the magnetic field first of all. So remembering that we draw field lines that describe the direction the north pole of a magnet would face if you placed it along one of these lines here. They exit the North Pole, enter the South Pole, and form these whole loops around the magnet. Like so. Notice they have direction. We know they're vectors, but we know vectors also have size. It's hard to describe the size of these lines here since they're all whole loops. In reality, if we wanted to draw the vector of the strength of the magnetic field here, the arrow there would be much larger than the arrows, say, up here, if we weren't drawing them in loops. So we need a way to describe the size of this magnetic field strength, and we use the term strength of magnetic field, the symbol a bold B, and the unit a Tesla, T. Closer to the magnet, we expect the number of Teslas to be higher, and further away we expect it to be lower. That's why if you push a magnet towards a bit of metal on a table, the magnet has to get to a certain proximity to that bit of metal in order to attract it. Or actually, it would be better to say this is another magnet here. So closer to the magnet, you get a stronger magnetic field. It's useful to think of the strength of the magnetic field, this is how my teacher used to describe it to me, as the magnetic field line density, or the crowdedness of the magnetic field lines. Far away here from the magnetic field lines we've drawn tend to space out. They're not crowded, and there's a low density. So we also expect the strength of the magnetic field out here to be lower than it is, say, right here, where all the field lines converge. Since these field lines are vectors, they have direction, and we often need to describe that direction in terms of the plane of the page. If I drew the magnetic field lines like I have here, that indicates they're going across the page. If I draw them as dots, that indicates they're coming out of the page. It's like an arrow has been launched from the opposite side of your computer monitor towards you, but the only part of the arrow that's pierced through the screen is the tip. If I want to draw them going into the page, I use crosses like that. And I like to think of this as the view you'd see if you had some kind of arrow with 4 feathers on the back that was stuck into the page, so it's being shot away from you. Let's talk about this term here, which is flux. It's got a symbol, I think that's psi, Greek letter psi. Or is it phi? Ooh, phi or psi? Phi or psi? I think that's psi. I think it's phi. Yeah, it's phi. And it's got a unit, Weber. And the strength of the magnetic field and flux are related, because flux requires I define an area. Say this loop here, this circle. Since that circle is sitting in a 3D space, you'd hope that some of the magnetic field lines of this magnet are passing through it. Flux is basically a count of those magnetic field lines. So if I have a uniform magnetic field, that's much easier. We'll say here, going or coming out of the page. And then I've got an area here. B, the strength of the magnetic field, tells me how crowded these magnetic field lines are together, and the area tells me the area which they're passing through, and if I multiply these two terms together, I get the flux. And flux is very important because if I change the flux through this loop, a current is induced in this wire in either direction depending on what I do to the flux. Weber. The Earth has a magnetic field around it, and the magnetic field lines point north like this. North, south, east, and west. So if I place a compass here and allow it to behave how it wants, you'd expect that compass needle to point north. But if I then introduce a magnet here with a north pole and a south pole, we'd expect this compass to also want to point its needle away from this north face, so like that. If you take into account both the Earth's magnetic field and this magnet's magnetic field, the needle ends up pointing something like that there, on a slant. We described the strength of the magnetic field as a vector. So if I have the strength of this magnetic field described by this arrow, and the Earth's magnetic field described by that arrow there, smaller, pointing north, to sum these two vectors together, I have to bring this arrow here, its tail to the head of the first arrow, and then draw a new arrow describing the tail of this first one to the head of the second one, like so. That's why you get this activity, this angle of this North Pole here. It tends to be that the values you'll get for the Teslas associated with the magnets you can hold in your hand are much stronger than that of the Earth's magnetic field. Unless I were to put this magnet far away, then I could feasibly have these two magnetic field lines of equal length, and I'd get the compass pointing at that right angle there.